Welcome to section 1.7. In this section, we're going to be looking at using our first order linear differential equations that we saw in the previous sections to work on some modeling problems. We're going to be primarily focusing on mixing problems. So mixing problems, the goal of these problems is to find the amount of a chemical in grams in a solution at a time t, or alternatively to find the concentration in grams in the solution at time t. So we've got a few different kind of formulaic things to take note of, some notations down here to look at. Our concentration of the solution is going to be the amount of the chemical per unit volume. So it's A of t over V of t. Volume is determined by taking the initial volume plus R1 minus R2 times T. This is where R1 is the flow rate into the tank. R2 is the flow rate out of the tank. So you can see on my diagram here, R1 is coming in, R2 is going out. So the volume is determined by however much there was to begin with, and then you take the amount coming in minus the amount coming out times T, so per unit time. Okay. C1 is the concentration of the chemical flowing into the tank. C2, again, is concentration within that total solution down in here. Okay. So these are the kinds of problems that we're going to be looking at in this section. Now, to see how we can relate this to the concept of derivatives and differential equations. So we have this rate of change, dA dt. So this is the change in amount with respect to time. That's going to be the rate of chemical in minus the rate of chemical out. So that's going to be R1C1 minus R2C2. But C2, we know from up here, is amount over volume, so A over V. So they can rewrite this R1C1 minus R2 times A over V. And if we rearrange this one a little bit, so we add this one over to that side, we're going to get dA dt plus, I'm going to keep the A off to the side here and group the R2 and the V. So R2 over V times A equals R1C1. And if you look at the general form of what we have here, this is a first order linear differential equation, right? The derivative, the first order derivative is right here. The non-derivative variable is right there, just the A instead of A prime. This right here would be the P function, so P of T. This over here is the Q function, so Q of T. So we can use our techniques and our tools involving first order linear differential equations to solve this type of problem. So let's go to an example of that. So a tank initially has 600 liters of a solution with 1,500 grams of salt in it. A solution with 5 grams per liter flows into the tank at 6 liters per minute. The mixture flows out at 3 liters per minute. Find the concentration of the solution after 1 hour. So we're going to need the volume, so V of t. And if you look back to the previous page, that formula, the initial volume, it had 600 liters in it, plus it's flowing in at 6 liters per minute and flowing out at 3 liters per minute times T. So we get 600 plus 3T for our volume. we're going to take that and sub that into the differential equation. So we're going to have dA dt plus R2 over V. So R2, that's the flow rate out, so that's 3 over what we just got, 600 plus 3T times A equals R1C1. So the rate coming in is 6. The concentration coming in is 5. So 6 times 5, 30. And we can simplify this a little bit. Just this one. Notice there's a common 3 in all of those. So we can go ahead and just take that out and cancel it. So we get dA dt plus 1 over 200 plus t times A equals 30. Now this is in the proper form for our first order linear differential equations. So we're going to need that integrating factor, I. So I is going to be e to the integral of p, so that's this coefficient right here, so 1 over 200 plus t dt. The antiderivative of this is ln of 200 plus t. We don't need absolute value on it because we know that the t value starts at 0 and only goes up into positives. So it's unnecessary in this case. E and ln will undo each other, leaving us with 200 plus t. And that's our value for I. So we're going to use that. So we get 200 plus t times A, all quantity prime, equals I times Q, so times 30. So we need to go ahead and integrate both sides of this. As always, this left-hand side, the integral and the derivative will undo each other. So we'll be left with 200 plus t times A. On the right-hand side, we have integral of 6,000 plus 30t dt. So we can go ahead and take the antiderivative there. And let me go ahead and we'll just do two things at once here. So we'll take the antiderivative, so that's going to be 6,000t plus 15t squared plus c. And then we'll divide this 200 plus t over so we can isolate A. So 200 plus t right there, which would give us a general solution to the differential equation, but we don't want a general solution. We want a specific particular solution. So we need to use some initial conditions here, or initial values. We know that the tank initially has 600 liters of a solution with 1,500 grams of salt. So 1,500 grams of salt, that is the initial amount. That's A that we're looking at here. So we need to substitute that in. So that's going to be A at times 0. So A of 0. That's going to be 0 plus C over 200 plus 0 equals 1,500 is how much was initially in there. So C over 200 equals 1,500. multiply that across. We get C equals, that's 30 and 4 zeros. 2, 3, 4. Yep. So we get 300,000. So our formula for A of t is going to be 6,000t plus 15t squared plus 300,000 all over 200 plus t. And then from there, double check and see what the question is asking for. It's asking for the concentration of the solution after 1 hour. So we're going to need to get the formula for concentration. That's going to be C2. So C2 of t, which recall from the previous page, that's A of t over V of t. So A of t is this big formula. V of t we found back at the top. That's the 600 plus 3t. So we're going to get 6,000t plus 15t squared plus 300,000 over 200 plus t. And then instead of making the complex fraction, I'm just going to combine the denominators here. So there's a 600 plus 3t. So this is the general formula for that concentration at time t, and we want it specifically after 1 hour. But remember, if we look back at the formula, everything in here has been put in terms of minutes. So we need to go ahead and use t equals 60 minutes instead of just using t equals 1. So 60 minutes. So that's 6,000 times 60 plus 15 times 60 squared plus 300,000 or 200 plus t, or excuse me, plus 60 times 600 plus 3 times 60. So if we just crunch these numbers really quickly here, so we're going to get 6,000 times 60 plus 15 times 60 squared plus 300,000 all over, that was 260, right? 200 plus 60 times 600 plus 3 times 60. So about 3.52, and we could simplify it to 595 over 169 if we're looking for an exact answer, but we get about 3.52. And this is a concentration, so this is grams per liter. So that would be our concentration. So all of this found by using our first order linear differential equations that we saw in the previous section. Moving forward into section 1.8, we're going to look at a couple new techniques for solving differential equations. So in this section, we're going to be talking about change of variables. So sometimes when we have differential equations that are a little more complicated than our separable or first order linear, what we can do is we can take that complicated differential equation, use a change of variables to make it simpler, and then solve it using one of our previous techniques. So the first up, we have a Bernoulli differential equation, has the form y prime plus p of x times y equals q of x. This is the same so far, except this is times y to the nth power. So we have a differential equation that is almost first order linear, except it has this y to the n power over here, where n is any real number other than 1. So because if this was y to the first, you could just recombine this over here, subtract it over, and then we wouldn't have this problem. Note, if n is 0, then this just turns into a big 1. This becomes linear. Okay, so it is very similar in form to the linear differential equation, but not quite. So in order to solve a Bernoulli differential equation like this, we have to use change of variables. To make it first order linear. So we're taking this differential equation that is not first order linear, turning it into one that is, so that we can solve it, and then we'll change the variables back when we're done with that process. So we're going to set u equal to y to the 1 minus n. So another way of writing that is u times y to the n equals y. So these are equivalent statements. Using derivative properties, we can apply the power rule to take the derivative of this. So we get u prime, you bring down the 1 minus n times y to the negative n, because we subtract 1 from the power, and then times y prime, so the derivative of the y, and that's a chain rule thing. So y prime, if we solve for this, is going to be u prime times y to the n over 1 minus n. Okay, so when we divide this under, we can move it and make it positive power up there on the top, divide the 1 minus n over here. Now we have some substitutions we can make, including the y prime. So we're going to take our Bernoulli differential equation and start substituting in these values. So substitute in, so we get u prime y to the n over 1 minus n plus p of x times u y to the n. Okay, and again, that's this one right here, equals q of x times y to the n. And the reason this substitution works so well is because now each of these terms has a factor of y to the n in it. Now we can just divide that away. So all that's left is u prime over 1 minus n plus p of x times u equals q of x. And then we need to clear away anything in front of the u prime in order to treat it like a first order linear. So that's u prime plus 1 minus n times p of x times u equals 1 minus n times q of x. And this result is first order linear. So this new version of the formula that we found in terms of u, so this is u prime plus some function of x times u equals some function of x. Now we can solve this as a first order linear differential equation. And then when we're done with it, we can switch it all back to y's at the end of the problem so that we have it in proper context. So let's try an example up at the next page. So solve y prime plus 2x over 1 plus x squared times y equals xy squared. So again, we have that form that's almost first order linear, except we have this y squared here. So we need to take note. So our n value is 2 in this case. So our u value is y to the 1 minus 2. So y to the negative 1, or just 1 over y. That's going to be our substitution. So when we change all of this over, so we're going to have u prime plus 1 minus n, right? So 1 minus n, that's 1 minus 2, which is just negative 1. So that's going to be, actually, we'll turn that plus into a minus then. So minus 2x over x, 1 plus x squared times u equals 1 minus n, so negative 1 times x. So just negative x on this side. Then from here, this is now first order linear in terms of u and x. So we need to go ahead and find I, that integrating factor. So that's e to the integral of negative 2x over 1 plus x squared dx. And that one, it would require like a u substitution to set this one up, but it works out e to the negative ln of 1 plus x squared, which then we can use log properties and move that negative up above the object. So it's e to the ln of 1 plus x squared to the negative 1. And now at this point, the e and the ln can undo each other. So we have 1 plus x squared to the negative 1, which is just 1 over 1 plus x squared for our I value. So we get I times u quantity prime. So that's going to be 1 over 1 plus x squared times u prime equals I times q. So just negative x over 1 plus x squared. So then when we integrate these with respect to x, left-hand side, of course, derivative and integral undo each other, as they always do. Right-hand side, this integral is actually very similar to this integral, just without that factor of 2 in there. So it works out the same way. You just pick up a factor of 1/2. So this becomes negative 1/2 ln of 1 plus x squared, and then plus c, of course. And just like the other problem in the last section, we don't need the absolute value because x squared will always be positive for all values of x, so we don't need absolute value. So then u, all we have to do is multiply the 1 plus x squared away to the other side. So u is going to be 1 plus x squared times negative 1/2 ln of 1 plus x squared plus c. Now, that would be the general solution if we were solving for u, but we're not solving for u, we're solving for y. So we need to put this back in terms of y again. So we go back up here, and we saw that u is equal to 1 over y up here. So in other words, we just need to take the reciprocal of this. So y is 1 over u, right? Because u is 1 over y, so they're just reciprocals of each other. So it really is just 1 over all of this. So 1 over 1 plus x squared times negative 1/2 ln of 1 plus x squared plus c. And that is our general solution to this Bernoulli differential equation, solved using a change of variables and a first-order linear differential equation. Now, there's one other type of differential equation to look at that also uses a change of variables, and that is a first-order differential equation called a homogeneous of degree 0 differential equation, or homogeneous, depending on your pronunciation of that word. So we say that this type of differential equation occurs if it has the form y prime equals f of x and y, where f of xy equals f of tx ty for all positive values of t, for which tx ty is in the domain of f. So if we can write the differential equation in a functional form in terms of x and y exclusively, and this relationship holds true, where the function f of xy could be replaced with tx and ty with no change to the function. If it obeys that property, then we say that it is homogeneous of degree 0, and then we can apply the technique we'll see on the next page. But let's just try a couple first, just identifying. So for this function right here, if we took f of tx and ty, that would be tx over ty minus 1. But that is not the same thing as x over y minus 1, and there's no way to make those the same thing. So f of tx ty is not equal to f of xy. So this one would be not homogeneous. But for one like this, for this function, if we took f of tx ty, we would get tx squared minus tx ty plus 2 ty squared all over 2 tx squared plus 3 ty squared. Notice every term here is going to get a t squared in it. We're going to be able to pull the t squared out of the top, and we're left with this, and pull a t squared out of the bottom, and we're left with that. The t squareds then cancel, and what's left is f of xy. So f of tx ty equals f of xy, found using algebraic simplification and manipulation. So this function is homogeneous So if we had this function set equal to a derivative set in a differential equation, we could actually use the process that we're about to describe. So if we are trying to solve a homogeneous differential equation, we use the following substitution. We have v equals y over x, or alternatively written as y equals x times v. We'll see them both used in different cases, which gives us y prime. If we apply the product rule to this, we get x times v prime plus v. Technically v times 1, because that's the derivative of the x, is 1. By applying this change of variable to a homogeneous differential equation, the result will be a separable differential equation in terms of v. So we're going to be able to set up and solve a separable differential equation in terms of v, and then we can switch everything back into y's at the end after the differential equation has been completed. So for this example, the first thing we want to check, so this is solve y prime equals y over x plus square root of 16x squared minus y squared over x. We want to check and make sure that it is homogeneous of degree 0. So we're going to take f of tx and ty. So that's going to be ty over tx plus the square root of 16 tx squared minus ty squared all over tx. So let's see here. These t's are gone, so that's good. This one we have a t squared and a t squared, and it's in the square root. So this is y over x. We can go ahead and pull the t squared out, so it's just going to be t square root of 16x squared minus y squared over tx. And then, of course, those t's cancel as well. So the result, we get y over x plus the radical over the x, which is the original. So this one is homogeneous. So we can use this substitution. We can apply this technique. So let me keep this off separated over here. So we're going to substitute. So y prime becomes xv prime plus v. On the right-hand side, y over x just becomes v plus the square root of 16x squared minus y squared. So that's going to be x squared v squared instead, over x. From here, we can go ahead and subtract off the v from both sides. So we're going to have xv prime equals square root over x notice also there is a common factor here of x squared in both of those. Factor it, and then take it out of the square root. So we're going to have xv prime equals x square root 16 minus v squared over x. Those will cancel. Now we're getting that look of a more separable differential equation. So let's turn v prime into the Leibniz form. So that's going to be dv dx equals square root of 16 minus v squared. So we need to move things around a little bit because dx has to come up and over here, which means this x is going to have to go with it, and the v's are going to have to come over here. So everything is kind of getting jumbled around a little bit. But this is going to be 1 over the square root of 16 minus v squared dv equals 1 over x dx. And now this is ready to integrate. On this left-hand side, this antiderivative is going to be, it's one of the inverse trig functions. So it's actually inverse sine. And the fact that this is a 16 instead of a 1 means that it's going to be inverse sine of v over 4. Equals antiderivative over here, of course, is ln absolute value of x plus c. And we only need a plus c on one side. It encompasses all arbitrary constants. And then from here, now that we've actually done the separation, we've taken the integral, now let's go ahead and turn the v back into y again. So v, we recall from up here, is y over x. So let's go ahead and put that in there. So this is going to be inverse sine of y over 4x equals ln and then the plus c. To get rid of the inverse sine, we need to take the sine of both sides, right? Because then it'll undo this. So we'll have y over 4x over here is sine of ln of absolute value of x plus c over here. And then multiply the 4x across. So we'll get y equals 4x sine of ln absolute value of x plus c. And that will be the general solution to this homogeneous of degree 0 differential equation, solved using the method of separable differential equations. So you can see that even when we get more complicated differential equations, we like to put them back into terms that we can use our previous methods for. That's a pretty common theme. But this brings us to the end of chapter 1, to the end of our introduction into differential equations. When we come back in chapter 2, we're going to be starting the linear algebra portion of this course, and that's going to take us through most of the rest of the semester. So looking forward to talking with you all when we get into chapter 2.